Hello, good to see you guys. And today let's talk about the rest of the elementary graph algorithms. So far we have covered the two kinds of search algorithms, breadth first and depth first. So this Tuesday we covered the DFS and we actually introduced you can say there are two types of basic implementations, iterative and recursive, and there is a advanced implementation or enhanced version of DFS. In the DFS, so the enhanced DFS is particularly important because it will be used to design and describe the two algorithms that we're going to talk about today. First is the topological sorts, and second, the strongly connected components algorithms. And the most important characteristics of the enhanced DFS is that we need to keep track of the discovery timestamp and finish timestamp for each vertex. So we will use a global time variable to record that global timestamp. And whenever it's the first time we visit a vertex, we will increment the timestamp and assign that new time step to that vertex. And when all the adjacent vertices are done, that means all the adjacent vertices are already visited, then the current vertex becomes finished. So that is when we set the finish time for that vertex. So you will see that how the starting time, the discovery time and the finishing time will be used in the two algorithms that we gonna cover today. Okay, so first of all, the topological sort is a very typical application of DFS. So this algorithm needs to take a directed or direct acyclic graph, and the acronym is DAG. Let me use the color pen here. Directed acyclic graph, and in short, it's DAG. So this graph should not just be only a directional graph, but also it shouldn't contain any cycles. So the acyclic means there's no cycles in the graph. And a intuition for acyclic, the concept of acyclic is that if you start from a vertex and you follow random edges, you work randomly in the graph. So no matter how you go, how you choose the edges, there's no way that you walk back to the source vertex, to the starting points. So if there's any path that forms the cycle, then this graph is not an acyclic graph. Okay. So the topological sorts takes such a DAG as inputs. And what this algorithm does is to reordering all the vertices, okay, such that if there's an edge from vertex U to V in the original graph, then in the reordering, the starting vertex U must appear before the ending vertex V. Okay, so I think in the next example, it's gonna showcase a more clear image of what this definition means. So it basically is an algorithm that helps to describe the precedence relationships. So a directed graph can be used to describe the dependencies or precedency relationship among events. Say I take the example from the textbook. So when you get up in the morning, there's several steps of things you need to do. You need to put on your undershorts, pants, shoes, socks, belt, tie, jacket, right? So all these events, they need to occur or happen in some sort of order, right? So the edges in such a graph kind of describe these dependencies. Like you must put on your socks before you put on the shoes. So there's a directed edge that indicates this temporal ordering relationship. And the shirts must come before tie, and the tie needs to comes before jackets, right? So the watch is a kind of a isolated vertex, which means I can put watch anywhere, right? I can move the watch over here, over here. It doesn't matter it doesn't interfere with other events. Okay, so such an edge from one vertex to the other means that the U must be put or must occur before the vertex V, okay? So if we run a typological sort on this graph, it will give us a much clearer visualization or much clearer description of which events should occur before the other. Okay. Say this is a typical result of running topological sorts. Okay. The graph, this is the original graph, and the parts here reordering of the vertices in the orange color is the is the results after running the topological sort. Okay, so all the vertices, they are ordered along a horizontal line. Okay, and more importantly, if you look at all the directed edges, all of them are pointing from left to right. Right, all the edges, all the arrows, they are pointing from left to right, and there's no edge that is pointing from right to left. Okay, so if you go given such a reordering, you can go from left to right to go through all the vertices without violating the rule that the vertex or the events that you come across first needs to actually occur before the before the events that's connecting. Okay, so if you go from left to right, you won't make a mistake because it's this ordering makes sure that all the edges are from left to right and there's no backward edges. So the topological sort algorithm that we're gonna look at will achieve such an outcome. So let's look at the implementation. It's quite easy in terms of lines of code, and it heavily relies on the DFS algorithm, the enhanced version of DFS that we implemented in the last lecture. Okay, so let's look at the code. There are just 3 lines of code. The first line of code, use the pen, is to call DFS on the graph, right? And we need to compute the finishing time, v.f, for each vertex in the graph. So this is the piece of information that will be used in the next line. So after each vertex is finished, right? Remember the process of running DFS on a graph. The vertex will start from white and then it becomes gray, right? And after all the adjacent vertices are done, it becomes black. So the moment that a vertex is finished, we need to insert it onto the front of a linked list. So this linked list will be returned as the results of the topological sort. And that linked list contains the reordering information of all the vertices. Okay, so it's actually just one run of DFS, and then we go through all the, then after each vertex is done, within that DFS procedure, we just take it out and insert it into a list. It's kind of a byproduct of running a DFS. So let's look at the example here. Given the results of the DFS, we have all the vertices annotated with the discovery and the finishing time. Okay, so let's find the vertex that has the earliest discovery time, which is here 1/8, which means short is where we start from the when we run the DFS, right? So it goes this pathway, tie, jackets, and when jackets is finished, we will mark the finishing time, and tie will be finished. So jacket here is the earliest vertex that finishes, right? It has the smallest finishing time. So jacket will be inserted to the front, to the head of the linked list. So this is what the second line describes. So whenever a vertex is finished, it will be inserted onto the front of the linked list. And the linked list is empty at the beginning, so jacket will be the first vertex. And tie will be the second that finished, so tie will be inserted here. And if you keep track of the finishing time, belt will be the third, right? And the shirt will be the fourth, and so on. So if you look at the finishing time in the results here, it's in a decreasing order, right? If you look from left to right, the finishing time is or basically all the vertices, they are sorted in a decreasing order of the finishing time. Okay, and in that we can see that all the edges are pointing from left to right. There's no edges that goes backward from right to left, and that's basically the amazing part, because DFS makes sure that all the ancestor vertices are finished later than the descendants vertices. So we will make more detailed analysis later. Okay, so let's see. Yeah, we have a more concrete example here. So now we use the same graph, but let's simply run a DFS on a different source vertex. So in the previous slide, we start from the shirt, right? So we'll show that the results of DFS are actually not unique. If you choose a different vertex as the source, the resulting graph the resulting DFS forest would be different. Okay, so for example, we start from undershorts. So the discovery time will be 1. And assume that we choose the pants as the second one, then the discovery time will be 2. And we go deep as possible, right? It's DFS. And the third one will be belts. And then will be jackets. Okay, so now jackets don't have any other adjacent vertices. So jacket will be finished, and then belts. And okay, we'll go to the shoes, because the pants has another adjacent vertex, shoes. Okay, and shoes has no more adjacent vertices. It will be finished. So pants will be finished afterwards, and then the undershorts, and so on. Okay, so for the socks, it is just one kind of isolated vertices. and watch and shirt to tie. Okay, so anyway, given the results of DFS, now let's look at the topological sort. So we choose the vertex that has the earliest finishing time, which is still jacket, right? I highlighted the finishing time here, which is 5. So we choose the next one, belt, shoes, right? And pants, and until we reach the last part, the shirts. Okay, and what if we connect all the edges, right? We'll see that this is a kind of different results as the outputs of topological sorts, which is different from the previous slide. But the principle, the rules is not broken. The rules still is true. We make sure that all the edges are pointing from left to right. There's no backward edges from right to left. So it basically shows that the results can be multiple types of results, and it is not like a unique results. And the reason, if you think of it in an intuitive way, is that as long as you make sure that the edges is from left to right, for example, you can, let me choose the pen. As long as you make sure that all the edges are from left to right, for example, I can take the sock, I can take this vertex and move it here, right? I can put the sock here, and the connection of the edge from socks to shoes is like this. The ordering is still from left to right, right? I can also move these. Let me use another color. I can also move these two, the shirt to tie, right? Make these two vertices. I can move them anywhere, like basically I can put them here, right, after the socks. But this doesn't break the rules because all the edges from shirt to tie and from tie to jackets, from shirt to belt, they don't break the left to right constraints, right? So yeah, so depending on the results of DFS, when you choose the different source index, source vertex in your DFS step, the resulting finishing time would be different. So the slightly different finishing time will lead to the different outputs for the topological sorts. All right. So we can look at the running time. So since last time we analyzed in our analysis, we know that the DFS runs in big theta of V plus E. V is the size of your vertex sets, and E is the size of your edges sets. So it is the topological sort is a kind of a byproduct. It happens within when DFS is being run. So it takes constant time to insert each vertex onto the front of the linked list. And when the DFS is done, the topological sort is also done. So they have the same running time efficiency. It's basically a DFS that you need to run. All right. So also we can like check the correctness of topological sort. Here is not a very strict proof of why topological sort is correct, but utilizing the knowledge about the edges, you will see that the topological sort actually, why it actually works. So we'll use the lemma. It's about that if the input directed graph is acyclic, okay, the constraint is that it is acyclic, and if and only if a DFS on the graph will yield no back edges. So the back edges in our last lecture, we have defined it to be the edges that points towards some ancestor vertex, right? So if an edge is pointing from a descendant to an ancestor, then we say it's going backward. So this lemma says if and only if there's no back edge, then a directed graph is acyclic. Okay. So if you look at the graph here, if there is an back edge, oops, then of course, if you can, sorry about that, if you go from pants to belt and jacket, then you can go back to pants itself. Then this violates our assumption that it is acyclic. Okay, so we can use this lemma to help prove the correctness of topological sorts. Okay, so the theorem that we want to prove is that the procedure in capital letters, topological sorts that we described can actually produce a topological sort of the input DAG. So these inputs contains the assumption that it is acyclic, right? So let's see the proof. So it suffices to show that for any pair of distinct vertices from U to V, actually any pairs of vertices U and V. So if the graph contains an edge that points from U to V, then we must have the finishing time of V should be smaller than the finishing time of U. Okay, so if we have a connection from U to V, if there's an edge, then the V must be finished before U finishes. Okay, so let's see. Let's look at different cases. So when the edge from U to V is explored, then V cannot be gray, right? So if V is already explored, V is already discovered, right? It's gray. And then if we explore the edge from U to V, then we are actually connecting to an ancestor, right? So that would be a back edge. So a back edge contradicts the assumption that the input should be a acyclic graph. Okay, so that is the first case when we first explore the edge U to V, V cannot be gray. Okay, so let's see the other two cases. There's only two cases left. So it cannot be gray, then the V can only be white or black. So if V is white, which means V is not explored before, then it becomes the descendant of U, right? So V is naturally the descendant of U, which means V will be finished earlier, right? Because it's DFS that we are conducting. We will not trace back until the descendant has no adjacent vertices. So that must be true. The finishing time of V must be smaller than the finishing time of U. Okay, and the third case is that V is black, okay, which means it's already finished. Okay, since we are still exploring from U, which means we haven't finished U yet. All right, so that means if we find V is finished and U is not finished, then of course this inequality also is also true. I'll say, okay, so combining these two conditions, we must have that if the graph contains an edge from U to V, then the finishing time on the right side must be smaller than the finishing time of the vertex to the left. Okay, so that kind of proves the theorem. Okay, so in the reordering, in the results, it is a reordering, right? Given any two vertices, it's always true that the finishing time of V is smaller than the finishing time of U. Okay, so that also shows that our strategy, our procedure is correct, because we take the when we do the DFS, whenever a vertex is finished, we'll take it out and we'll make sure that it has the smallest finishing time so far. Okay, so that's the correctness of this algorithm. Alrighty, and I would suggest you to first go through the topological, go through the lemma here in the textbook, and then I think the textbook put more text, have more paragraphs in describing the correctness, but it's basically the analysis of the 3 cases. Alrighty, and we are now done with the first algorithm, or it's quite a practical application of the DFS algorithm. Okay, so I can put a more concrete example for why topological sort is useful. So, for example, when you in a software development projects, software engineering projects, the package that we are writing depends on a lot of other packages. So such a dependency can be described by the topological sorts results. Like we want list all the packages so that the one that we first listed is always the required by the ones that comes in at the later stage. So we don't want any backward dependency conflicts, right? We can always make sure that the most important packages is always on to the left. So we can make sure that the installation or the package calling procedures steps is not messed up. Okay, that's topological sorts done. So now let's look at a second application of depth first search DFS, which is called the strongly connected components problem. So this is a very classical problem, and it applies to the graph, and it basically decomposes a directed graph into several components. And these components, they are within themselves, they are strongly connected. Okay, so many other algorithms relies on such a decomposition. So in a lot of problems, we can decompose the graph into several strongly connected components, several SCCs, and the other algorithms can be applied separately on each component, and then we can combine the solutions together. Okay, so a strongly connected components can be be viewed as a super node, as a super vertex that contains a lot of vertices in the original graph, and these sub vertices, they are mutually connected within the current components. Okay, so it provides kind of a higher level description of the topological structure of the graph. So let's look at a more formal definition. So we say a directed graph is strongly connected if every 2 vertices are reachable from each other. Okay, so it is a very strong condition. It's emphasized that if you take any 2 vertices out, they must be reachable from each other. Okay, so it's emphasized the mutually reachable relationship. Okay, it is the strongly connected components of a graph are actually a subset of vertices that can be mutually reachable. Okay, so for example, if I show this graph here, we have 6 vertices, then we can simply count how many strongly connected components are there in the in this graph. Okay, so first of all, if you look at the graph as a whole, then of course it is not strongly connected, right? So if you take the vertex 1 and 3, then they are not reachable, right? They are not connected. So actually, this graph has 3 strongly connected components highlighted by the different colors. The first part, the blue part, is 1, 2, 4, 5, and the 3 and 6, they are 2 strongly connected components here. So it may be confusing at first, but the 3 and 6 together, they do not form an SCC because only vertex 6 can reach 3, but not the other way around. 3 cannot reach 6, but 6 can reach 3. So it is not a mutual connection. It is not a mutual. There's not 2 edges. So if we add 1 more edge from 3 to 6, then 3 and 6 can be kind of a strongly connected components. Okay, so that is the condition we need to look at here. And a formal definition for a SCC of a graph. Here it says an SCC of a graph is a maximal set of vertices. Okay, so the C is a subset of all the vertices V in the original graph, and such that for every pair of vertices within these subsets, we have both a path from U to V and a path from V to U, and they are mutually reachable. So here we introduce some notation here, the curly arrow from U to V and the curly arrow from V to U. So this curly wave like arrow is not an edge, is not a direct, it may be an edge, but it is not necessarily an edge. There could be some intermediate vertices. So you can reach V through some like other A or B or C vertices, but eventually it will reach V. So this curly path indicates such a relationship. And also the from V to U also mean the same thing. There could be some other intermediates X, Y between the path from V to U. Okay, so if we make sure that for every pairs within C, the 2 vertices, they are mutually reachable from each other, then we say this subset is a strongly connected components. Okay. All right. So in terms of the problem question of how to obtain the SCCs, we need to prepare ourselves with some other notation here. There's an important operation called the transpose of a graph. Okay, it's actually a very easy notation. So given the graph, we will apply we can say that a transpose is defined by flipping around all the edges. Okay, the transpose of the graph GT is the result of flip around all the edges. Okay, so originally the graph, the edge from V to U is in the original set of edges E, but here we just exchange the starting point and the ending point, the starting vertex and the ending index. We make it U to V, right? So we just exchange the direction of flip the direction of the edges, and we do that for all the edges. And the resulting new graph is something we call the transpose. Okay, so the directions are all reversed. Okay, and the running time for creating a transpose is also big O of V plus E. Okay, so here's the transpose is something we need to know about before we compute the SCC. Now let's look at the algorithm to compute or to find all the strongly connected components in the graph. It's basically three key steps, and the last step is just to output the results. The first step is to call DFS on the graph. Okay, so the DFS is still the enhanced version of DFS, which records the discovery time and the finishing time for all the vertices. Okay, so here it emphasized that we need to compute the finishing time for each vertex. Okay, so that's first step to call the DFS, right? And second step, it's also clear. It's to compute the transpose of the graph. Okay, we reverse all the edges. Okay, and the third step, it's interesting, is to call DFS again, but on the transpose of the original graph. When all the edges are reversed, then we call DFS again. Okay, and the interesting or the tricky part is that in this second round of DFS, we need to make sure that in the main loop of DFS, we need to consider the vertices in order of decreasing finishing time. Okay, in the second round of the DFS, each vertex is already has a finishing time that's from the first DFS, right? So in the second round of DFS, we need to consider all the vertices in the decreasing order of this old finishing time. Okay, so that is the tricky part, because we need to remember the finishing time of the first DFS, and then when we run the second DFS, we need to use that old finishing time information to carefully select the vertices in our loop of DFS. Okay, so we'll look at some demos here. So the highlighted sentence here, consider all the vertices in the decreasing order of finishing time. So this is this consideration should happen here in the in the main body of the procedure here, in the for loop here, right? So this is the DFS, and DFS calls DFS visits. In DFS visits, there's also a for loop. So this consideration or this constraint needs to satisfy in both for loops. In the first for loop, when we iterate over all the vertices in the graph, and we need to select the vertex that has the highest finishing time first, because we want to make sure it's the decreasing order of finishing time. And in the body of DFS visits, there's another for loop, right? When we go through all the adjacent vertices, we also need to follow the principle that we select those that has the highest finishing time first, and in decreasing order. So next, let's see why this is the case. All right, okay, I forgot to mention the last line of code. It is just to output the vertices of each tree in the DFS forests. Okay, the third line, line 3, the second DFS will result in a DFS tree, a DFS forest. Then all the trees in the DFS forest can be treated as is just the separated, strongly connected components that we want. Okay, so I think let's directly go through an example, and it'll be much easier to digest the algorithm. Okay. All right, we have a graph, directed graph with 8 vertices. Let's call it a G, graph G. So remember, we need to call DFS on G. So, and all the finishing time will be recorded, will be saved. Okay. We assume that we start from the vertex C, right? And we will anyhow just call DFS. And Also, we can remember all the tree edges, right? The DFS will result in a forest of trees, and all the edges will be all the tree edges are highlighted. Okay, so most importantly, we need to remember the finishing time, because the finishing time will be used in the next step. Okay, and the next step is to compute the transpose, right? We reverse all the edges and we'll get the transpose. Okay, the transpose is like, if you pay attention to the edge here, now here it is from B to A, but originally it's from A to B. So all the edges, look at all the edges, they are reversed. So this is the result of the transpose of the G. And the third step is to call DFS again on this transpose of the graph, but we need to consider all the vertices in decreasing order of the old finishing time from the previous DFS. Okay, so now let's step into this, the second run of DFS here. Let's go to the next slide. All right. So keep in mind that now we are analyzing the second DFS on G transposed. Okay, but the old information, the old finishing time information, I pasted here because we will use that. Okay. So because we will need to make sure the decreasing order of the old finishing time, that means we need to select the vertex that has the highest finishing time as our start, right? Which is the vertex B. So B will be the first vertex that we start with in the second DFS. Okay, so we will record the discovery time here. B is the first one, and A will be the second, right? And E, and go back to B. Okay, because remember now the edges are reversed, so there is a connection from B to A. Actually, A is the only adjacent vertex of B. So we actually have no other choices. So we will choose A. And when A is done, we need to follow the edges to E and then to B. And then after E is finished, we'll finish A and then finish B. Okay, so that's the typical DFS. Okay, so that's one DFS tree formed, right? So the next one is something that we need to pay attention to, because we need to select a different vertex now. Since the B is selected, the B is discovered, A is discovered, E is discovered, right? Now we need to choose from the remaining vertices, and we need to choose the vertex that has the highest finishing time, which is C. So C will be finished, so will be chosen here. C will be discovered first, and then D, right? After D is finished, C is finished. All right. So next, we just follow the same principle. We need to choose G because G has the biggest finishing time here. And G leads to F, and then last is H. So that's when the second round of DFS is done. So if you look at the results of the DFS, it produces 4 depth-first trees, 4 DFS trees, and the tree edges are highlighted. Okay, so 4 trees, and they correspond to the 4 strongly connected components. Okay, the resulting 4 DFS trees highlighted by the colors here, they are exactly the SCCs that we want. Okay, and the algorithm is now done. Okay, so the 4 strongly connected components are 4 sets of vertices. They are A, B, E, C, D, F, G, and H. H alone itself is a set. Okay, and more importantly, the SCCs of the original graph and the transpose, they are actually the same. They remain the same because they are the set of excuse me, the set of vertices. According to the definition of SCC, they are just a bunch of sets of vertices. So even though the edges are reversed, the strongly connected components don't change. We'll have some analysis of the correctness of SCC algorithm in the next few slides. Okay, so you can see that the interesting part is that after the second run of diffs done, we will obtain some trees, and those trees, they can be directly used as the strongly connected components. And if we examine the relationships of all the vertices inside those SCCs, we can see that indeed they are strongly connected to each other, right? We just randomly, for example, randomly look at the blue region here. The A can reach B, right? The B can also reach A, so they are mutually reachable from each other. And the F and G is also mutually from each other. C and D, right? And H mutually from each other, from itself. But if you look at the connections here, it's basically a one-way connection, right? There's no cycles. There's no mutual reachable relationship. So the resulting trees are indeed the SCCs that we need at the beginning. Okay. So again, let's look at the transpose versus the original graph. We'll see that they have the same SCCs because when you flip around, when you reverse the edges, it doesn't change the strongly connected components property. Okay, so with these SCCs computed, with the forests computed, we can kind of have a more compact view of the graph, which we call a component graph. And this component graph is a kind of more higher level summary of the graph by combining all the strongly connected vertices together as one vertex. Okay, so we call this a component graph. If you think of all the blue vertices as one vertex, and all the two green vertices as one green super vertex. So it's basically a shrinked or a condensed version, right? So if you think of all the vertices in the blue here, let me use the different color. If you think of these three as just one vertex, right? All the red ones, orange ones as one vertex. So it will result in a much compact view of the graph. So you can think of a group of vertices as a components, and all the edges that connecting them actually are the same, right? All right, so this type of summary or descriptive information of the graph is very useful, especially when you want to study the relationships of the vertices in the graph. So it could be if it's a social network graph, then you can see how people group together, and within some groups, people are more mutually connected, while it's outside the clan, outside the group, then there's less connections. Applications like that are quite commonly used. Okay, so now let's analyze a little bit of why the algorithm we propose is correct. Okay, so why running 2 rounds of DFS, especially in the second round of DFS, why it is the case that as long as we follow the principle of the decreasing order of old finishing time, we will make sure that the resulting DFS trees are the SCCs. So we'll look into that. Okay, so it's optional, but I think it's really helpful for you to understand the outcomes of DFS and why this is the case. So let's consider the first lemma. Okay, so it considers 2 distinct, strongly connected components in a graph. Okay, C and C prime. So let's assume U and V are in C, and the U prime, V prime are in C prime. Okay, and we assume that these 2 components, C and C prime, they are connected using a path from U to U prime. Okay, so the notation appears again. So the path means that there's some direct or indirected interpolated connections between U and U prime. Okay, and then this lemma says if there is a path from U to V, okay, as indicated by the connection here, then there cannot be a path from V prime to V. Okay, so we'll see why this is not, so why there shouldn't be a connection from V prime to V. Okay, so assume that if the so if there is a path from V prime to V, right, then which means I can go start from U prime to V prime and to V and to U. Okay, so this means that U and U prime, they are mutually reachable. Okay, so which contradicts the assumption that C and C primes, they are strongly connected components, because we assume that C and C prime, they are 2 SCCs. But if U and U prime, they are mutually reachable from each other, then that means the 2 SCCs can actually be merged, right? It's actually just 1 SCC. Okay, so that's our conclusion. So there shouldn't be such a connection from V prime to V. In another language, the connection between 2 SCCs must be a one-way connection. Okay, so there can be a connection from V to V prime, but in the opposite direction. Okay, so there can be a direct connection here from V to V prime, as long as it is in the same direction as U to U prime. Okay, but there shouldn't be a two-way connection. As long as a two-way connection, then these 2 SCCs can be merged. So that's our lemma 1. We will use that lemma 1 in our next proof. Okay, so now let's extend the notions for discovery and finishing time a little bit. So because the discovery time and finishing time are referred in the advanced version of DFS, right? So each node will be assigned with a D time and an F time. So we can also define a starting time and a finishing time for a set of vertices, okay? And we let the discovery time of the set to be the smallest discovery time of all the vertices within that set. And the finishing time be the maximum, be the latest finishing time of all the vertices within the set. Okay, so we always choose the earliest starting time and the latest finishing time in the set. to indicate the whole sets. So for example, in these four sets, C1 to C4, the starting time for C1 is 11 because it is the smallest finishing time, smallest starting time. And the finishing time is 16 because 16 is the latest finishing time in the subsets. And we can do the same thing for all the components for all the sets. So this notation would allow us to say that, okay, we can allow us to define the discovery time and the finishing time for strongly connected components. Okay, so we will introduce a second lemma. So this lemma says, let the C and C prime be two distinct SCCs, and suppose that there is an edge from U to V, and U is in C and V is in C prime. Then we must have the finishing time of C is greater than the finishing time of C prime. Okay, which says, okay, if we examine this in the previous in the same graph, the finishing time of F is 16 right here, right? And the finishing time of C2 is 10. Since there is a connection here, right? There's a connection from C to C1 to C2, then this equation is satisfied, right? 16 is greater than 10. If we check this one, there's a connection here. So the finishing time of C3 is 7, and 16 is also greater than 7. Okay. If you check the connection here, C3 is connected to C4, so the finishing time of C3, 7 must be greater than 6. Okay. So this is the second lemma about the finishing time. It describes the relationship between the finishing times of SCCs. Okay. So let's see how the lemma 2 is proved. Okay, so we consider two cases depending on which SCC has the first discovered vertex during the first DFS. Okay, so if C is first discovered, then it means there will be some vertex in C that's first discovered, right? So the discovery time for C should be smaller than the discovery time of C prime. Then X must be first discovered. So by the time X is first discovered, all the vertices in C and C prime are undiscovered. Okay, so because there's a path from U to V, then that means all the vertices in C prime are also the descendants of X. Okay, so in a DFS tree, any descendant vertices must have the earlier finishing time than the ancestor. So X is the ancestor to all the vertices to C prime. Then that means X has a latest finishing time. So we must have the finishing time of the whole set C should be greater than the finishing time of C prime. Okay, so that's why lemma 2 is correct. Okay, and in the second case, if C prime is first discovered, right, then that means the discovery time of C is greater than C prime. So all the vertices in C prime become the descendants of Y. Okay, so the finishing time of Y is the finishing time for the whole set C prime. And since there's no edge from there's only one edge from C to C prime, then according to lemma 1, there shouldn't be a connection from C prime to C. So that's the one-way connection lemma, right? There shouldn't be a two-way connection. So that means no vertex in C is reachable from Y. So by the time Y is finished, all the vertices in C is not discovered. Okay, And that also means the C should have, the vertex C should, the whole set C should have later finishing time than Y. So analyzing these two cases, we have shown that the lemma 2 is proven, which says the finishing time of C must be greater than the finishing time of C prime. Okay. All right. Then we will use a corollary of lemma 2, which tells the same thing as lemma 2. So it says if the there's an edge U to V in the edge, in the transpose of the edge, and U is in C and V is in C prime, then the finishing time should be of C should be smaller than C prime. Okay, I think this is straightforward because a transpose just flips the U and V around, right? So if it's a transpose, and that means the finishing time of C prime should be greater than C. It's just the reversed version of lemma 2. Okay. All right. Finally, let's see why the SCC algorithm will work. Okay. It's a bit dense content here, but I hope you can go through the slides several times and read the corresponding part in the textbook. I'm sure that you will have a better understand of the correctness of SCC algorithms. So when we perform the second DFS on GT, we start by selecting the component that has the maximum finishing time, right? We make sure that we select the vertex that has the maximum finishing time. So the search will start from some vertex X and visit all the vertices in C, right? We assume that we will start from X in our second DFS. So by the corollary of lemma 2, the G transpose should contain no edges from C to any other SCCs, right? Because that will create a two-way connection. Okay. So because FC, the finishing time of C, is the maximum, so there can only be edges from other SCCs to C, but no edges come out from C. Okay. So that is the results of applying lemma 2 and its corollary. All right. And therefore, the second DFS will not visit any other vertices outside the C. So the DFS tree rooted at X will contain exactly all the vertices of C. Okay, that's why we can use the resulting tree from the forest as the SCC, because the tree will not, we will not be able to visit other vertices in other SCCs, because there shouldn't be vertices coming out from the current strongly connected component C. Okay, and then assume that there are two vertices here. There are three SCCs here because C is done, C is finished. And the second DFS will select some vertex in C prime. For example, it's Y. But since C is done, so we will not go from Y to C. And since there's no connection from C prime to C prime prime, so C prime prime will also not be reached. Okay, so C prime will be the second SCC discovered. Okay, and after C prime is done, then C prime prime will be done. Okay, so by running the second DFS on all the components, we make sure that okay, the resulting trees from the forest is just the SCCs that we are looking for. And in conclusion, the SCC algorithm is correct. And hopefully that gives you a better sense of the correctness And I understand that it is a bit I'm proceeding a little bit fast here, but I hope you can read the contents, the slides yourself, and the corresponding book chapters. So the SCC is quite important in analyzing the network structures. It's useful in finding communities, clans in social network, and also it is used in search engine in grouping or finding highly related, highly cited web pages that can be classified as a same category type of information. So it's a pretty commonly used algorithm. Okay, and that's the 2 algorithms that we covered today. And that is also the last lecture on the elementary graph algorithms. So from the next lecture on, we're going to cover some more advanced graph algorithms. And yeah, thank you for coming.